are going to try to understand something called controllability. So let us say our system is x dot is equal to ax plus bu. Can we always choose some suitable u that takes the state from initial x1 at t1 to desired x2 at t2? That's the question. Okay, so when we think about the solution of this system, you will see that there is a complementary solution and a particular solution. That's the general solution. So what we can do is we can say initial condition is x1. Forget the t1. It's an autonomous system. It does not have time explicitly in it. So we can take t1 equal to 0 with no loss of generality. So now some x1 is given. What we can do is we can take x dot is equal to ax x naught is equal to x1, okay, and then we will get a solution which we will call, let us say, x bar. It is the complementary solution. Okay, now separately we will do x dot is equal to this x0, I mean the initial condition, this x0 here, and this x dot is equal to ax plus bu. X0 is equal to 0, and this will give us a particular solution, and the final solution, complementary plus particular, this will have initial condition x1. Okay, so that is how the solution can be looked at. Now we want it to reach a desired state. For it to reach that desired state, what we can think of is an error. So we will say let E be equal to x1 minus x2, right? So then I'm sorry, not x1 minus x2, I mean x minus x2. Okay, this is a fixed quantity. Okay, so then x dot is equal to ax plus bu, and then we have E dot is equal to x dot is equal to a E plus x2 plus bu, and so you see E dot is equal to ae plus ax2 plus bu. Okay, very good. And then what we will do is the initial condition for E at 0 is x1 minus x2, and so from this we will find a complementary solution, and that will evolve and it will have some value at t2. This will just be a constant, so it's like forcing. This will have some value at t2, and this will lead to another one. We want it to negate the sum of these two values so that E at T2 becomes 0. Okay, so you will see that since this x2 is arbitrary, basically what we need is, can we find some function u of t such that at some time t greater than 0 we can make the solution of x dot equals ax, ax plus bu x of 0 equals 0, starting from 0 initial condition, right? We can make the solution of this such that x of t equals xd for any desired xd. This is the question. If you think about it, you will see if we can achieve this, then we can achieve that. Okay, how do we achieve this? So we start from 0. Okay, so start with initial condition for x equal to 0, want to reach xd at time t. Okay, here is our equation. X dot is equal to ax plus bu. That means x double dot is equal to a times ax plus bu plus bu dot, which is equal to a squared x plus abu plus bu dot. X double dot, then x triple dot is equal to a cube x plus a square bu plus a bu dot plus bu double dot. When I put a bracket here, I mean the nth derivative, the nth with the round brackets here. This is equal to a to the power n x plus a to the power n minus 1 bu plus a to the power n minus 2 bu dot and so on, plus bu, I think I have made n minus 1. Okay, all right, so we've got this far. You may wonder why we are not taking more. That is because you see a to the n can always be written in terms of lower powers. Remember the Cayley-Hamilton theorem. That is one reason why we need not take more, but I am going to be a little light-footed on that and not get mired down in it. So what we will do now is we will think of this as a Taylor series for x, and we will write it like this. Remember, x starts with 0 initial condition. So x, we use a different color, x is equal to x0 plus x0 dot times t plus x0 double dot times t squared by factorial 2 plus dot 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 plus x n t to the n by factorial n plus more. Okay, so that's true. And what we will do here is we will come here and try to collect these pieces. So you will see this one, the initial condition is 0, right? So all that remains is this one here, and then this one here, and then this one here, and so on. And that is why what we have here is a to the n minus 1 b times some function of t. Let me just write it as 1. This is a product, some function. It has all the u's and derivatives and many expansions and so on, but that is the most, finally it just works out to be something like this, plus a to the n minus 2 times b times some f2 of t, which depends on the u's, and so on until we have some b, and that is times something, some fn of t. Okay, now what I'm going to do is I'm going to put t equals capital T, and then what I will end up with is this matrix a to the n minus 1 times b. Think of it, if b is one column, then this is just a column. If b is two columns, then this is two columns, but I will just put a spacer here. Then I will put a n minus 2 times b, a n minus 3 times b, and all the way until b, and then now I will think of these as numbers because I'm evaluating at some time. So I'll have some f1, f2, fn, and I want this to be equal to some desired value, right? So let's say I want it to be some arbitrary xd. When will a solution exist? A solution will exist if the rank of this is n. So I will admit that I have been a bit hand waving, but this is called the controllability matrix. Okay, if this controllability matrix has rank n, if it is full rank, then system is controllable. That means in any desired time interval not 0, I can take it from any initial state to any desired final state. Subsequently, what it does is a different matter, but from t1 to t2, I can take it from any state x1 to any other state x2. Okay, and if this is not full rank, well, you may ask, can the rank be more than n? It can't, right? This has n elements total. It has n rows. The rank can't be more than n. If B has only one column, then it has n columns also. But if B has two columns, then it has 2n columns. But in any case, the rank cannot be more than n. Okay, so if not full rank, that means rank less than n, then system is not controllable. Okay, so this is the controllability matrix. Let us go to MATLAB and see some implications. Okay, so let us start with A equals some random 5 by 5 matrix. Let B be this, so just 1 and then zeros, and let us say I want to assign some eigenvalues to the system. Okay, so let us look at A. So these are the eigenvalues, right? 3 are in the right half plane, 2 are in the left half plane. This is some system. Now what I will say is, I will say u is equal to minus kx. Okay, so this is now different from the polynomial things I was doing there, but so what we will say is application to x dot equals ax plus bu, u equals minus kx. That means without control, we have the eigenvalues of A without control, and with control we have eigenvalues of A minus Bk, and these may be things that we like. We can put them where we want them. Okay, so let's come here. Let us choose some eigenvalues arbitrarily. So for example, I will say E equals minus 1, 2, 3, 4, 5. Just to show you that they are quite arbitrary, I will say K equals place. This is a built-in MATLAB command, A, B, E. So it gives me some K. These numbers happen to be a bit large, but that's okay. Then I will say the eigenvalues of A minus B times K, and you see it is minus 1, minus 2, minus 3, minus 4 and minus 5 as desired. In this way we can place them wherever we want. We can place complex poles also. We can say K equals, if we have repeated poles, it's a slightly different matter. This command may not work, but there are other ways to do it, but let us not go to that yet. K equals, let us say minus 2 plus I minus 2 minus I. See, complex conjugate pairs. Minus 3 plus 2 times I minus 3 minus 2 times I. Let us say these are our desired poles. In that case we will say, not K, E equals, sorry, these are our desired poles. Then I say K equals place, once again that, and now I have some other values for K, and then I say the eigenvalues of A minus Bk, and you see those are the eigenvalues, minus 3 plus minus 2I, then minus 2 plus minus I, and then minus 2. Okay, now let us see this matrix here. Let me call it C, controllability matrix, is equal to A times A times A times A times B, A times A times A times B, A times A times B, A times B, and B. Okay, so that's the matrix, and I can look at it in different ways. I can ask for the rank of CC, and it will tell me that it is 5. You may not like to use the rank command. There is something called the singular value decomposition. You can look at SVD of CC and see if the smallest one is much smaller than the biggest one. Now the smallest one is pretty small. I mean, that's about 5 and this is about 0.015, so it is pretty small, but in terms of numerical work it is not small. In terms of a physical system, that's not very good. That's a different matter, but mathematically it is clear that this has this is invertible. We can also do the determinant. I don't recommend it as a numerical check, but in exact mathematics it is all right, and you will see that it is a small number, but it is not terrifically small. I repeat, the determinant is not a good way of checking rank, but this is not a numerical linear algebra class. We can take the inverse of C, and you will see there is an inverse, answer times CC, identity matrix. So C is invertible, it has full rank, and so I am able to place the eigenvalues wherever I want. Now let me take a different example. This A is a diagonal matrix. Now remember B. In B I have only one here, right? So intuitively you know that with the input I can affect the first state, but the first state is not coupled to any other state, and therefore I can't control any of the other states. Okay, so then what happens? I try to place these eigenvalues, right? So I say K equals, and it gives me an error, right? And it says nearly uncontrollable. In fact, it is not nearly, it is quite uncontrollable. Okay, so it could not place the poles at the specified locations. All right, suppose I say A 1 to 4 equals rand 4. Okay, so now you see I have these 4 states are coupled, but the last state is not coupled. B only affects the first state, but the first state is coupled to the second, third and fourth states, but not to the fifth state. Not directly, not indirectly, nothing. There is no way to affect the fifth state. So we think that it will not work even now, and we can see that. We can say K equals place, and you see it can't place the poles. Now let us say CC equals, and let us look at the SVD of CC, and you will see that one singular value is exactly 0. We can look at the determinant of CC, that works out to be 0. We can look at the rank of CC, and that is 4. So it is not controllable. Okay, when it is not controllable, we can't place the poles wherever we want. The eigenvalues may be such that the system is stable. We may be able to stabilize the system, that's a different matter, but we are not able to place the poles exactly where we want. Okay, so that's the controllability matrix. Once again, let us go back here so that you can recall. So that's the controllability matrix here, green. Okay, if the controllability matrix is full rank, then we can make the state go from anywhere we want to anywhere we want within a finite time. And in particular, what that means is, although putting eigenvalues only refers to infinite time behavior in a way, but it also means that we can place the eigenvalues wherever we want. It is possible to think of a solution. It is possible to think of a solution in finite time, but that I will discuss in the class during our meeting rather than put it in a lecture. Okay, so we have now finished our discussion of controllability. I hope you will agree this is a restricted system. It's linear, it's constant coefficient, but it's an absolutely marvelous concept, and this is a very critical idea in control theory. It is due to Kalman, who made fabulous contributions to control theory in the last century, 60, 70, 1960s, so you can know when it is. Okay, thank you. I will continue with observability later.